Welcome back to Fundamental of Electrical Circuits series. This time we're going to talk about op-amps, just introducing you to a new component. It's called op-amp. Op-amp, unlike resistors and power supplies and other components that we've discussed so far, it's not a basic element, but rather is made out of a lot of transistors. We're not going to cover op-amps in its full detail in terms of individual transistor, but we're going to look at it as a whole and what it can do for us. Op-amps are a very, very useful device in building all kinds of devices, including amplifiers and other things. So op-amps, the basic form of op-amp we're going to work with, it's going to have two inputs. One is going to be called the inverting input, and we're going to assign, usually we refer to the current at this point as IN to indicate it's a negative side, and the voltage, even though we don't show it, there is always a reference. So the voltage, when we say VN, which is the voltage at the negative side, it's really going to be voltage difference between that and that ground that we're not showing on the circuit. And then this is called the positive side of it, or the non-inverting side of it, and we're going to use IP to refer to that, and just like the VN, we're going to use VP to refer to that. These are standard way we talk about op-amps. Now, these are called positive bias and negative bias, usually written in V+. In order for the op-amp to work, we have to have power supply deliver constant power to it in the form of positive bias, and we'll talk about what the rail portion means. Sometime you may also see V plus written as VCC and then V minus written as VE. Okay. Now, an op-amp, if you don't connect anything to it, or it would operate more or less in this form. On this axis, we have the difference of the voltage between VP and VN. So that would be the difference from here. It's going to be plus here, minus here. So this is going to be VP minus VN, and of course V out is over here. So on the vertical axis we have the output. On the horizontal axis we've got the VP minus VM. So that's considered, that's more or less the difference is considered the input, and V out, the difference from here to that reference that is not shown, is going to be considered the V out. So this is the V out and the vertical axis. So if you notice, what's going to happen is that there is a space which is called the linear region, this section of the curve. So as long as the output, and also the output is basically equal to this open, some number, we don't know what that is, it's very large usually, but this is called an open loop gain, meaning that if there is no feedback from output to input and you run it open, output is going to be this open loop gain, the A, multiplies by VP minus VN, which is the difference between the two inputs. Now, as long as the output is between VCC, the positive rail, positive supply you're providing, and the negative supply you're providing, this is going to go linearly according to A. So A is going to be the slope of the curve as VP minus VN grows and shrink. Once it hits either one of those limits, it flattens out. In other words, that's what the rail means. It's basically these are the ceiling and the floor for the V out. So V out can never go below the negative number, never gonna go above the positive number theoretically. In practice, I can't even get close to it. It's gonna be about 1.6, 1.7, depending on what product you're using. It's between 1 to 2 volts. Before it gets to that point, it will stop. But for our problems we're gonna work on, we have to watch out that the V out, if our V out goes above this value or below this value, we have to limit it because there's no way for it to go beyond that. So we have named for this area this area is called the negative saturation. Sometime you might also hear people refer to that as a cutoff region. This area is called positive saturation, or sometimes simply saturation. If you go above VCC, just saturate, it won't go anywhere above it. And this region is called linear region. Now, if you're designing computer systems and digital system, you want to either be fully saturated or not saturated. You like to be staying mostly in the negative saturation or saturation. You want to have a small linear region. If you're designing amplifiers, sensors, filters, things like that, you of course want to mostly stay in the linear region, but because once you get to cut off a saturation, nothing interesting will happen. So that's the essence of it. Now, I just wanted us to take a few minutes and look at an actual part and just give you some of the data on this one. The open gain for this thing is 10 to the 5, so 100,000. And some of the other numbers sometimes you may need are in is usually 2 mega ohms. That is the if I put an ohm meter across this port and this port to measure the resistance, that's called Rn. And if I look from the out port to ground and measure the resistance, that's called Rout. And Rout is usually about, I believe in this one would be 50 or 75 ohms, somewhere in that range. Okay, so, and it's called quad because there are 4 of them. It might be worthwhile for us to take a look at the datasheet. I will not go to the datasheet in very detail, but on engrcs.com under the components, we do have a datasheet. Of course, you can also Google it if you want and get the same thing. Every IC or chip that is out there will have a datasheet that describes everything in detail. Most of the time in lab we use most of the time in lab we will use the DIP package, which is this one. If we were building manufacturing in a manufacturing environment, we probably would have used one of these surface mounts there. But here we probably use it. And they're called quad because if you look at it, there are 4 op-amps in here. If you notice, they're independent of each other, and if you see, it's got a VCC and it's got a VEE. And if you want to know how high the positive bias can go, you can put as high as 32 for the 324, and you can go as low as for this one, low as ground. Usually, it's what we do. Now, if you want to have positive and negative, you have to go plus minus 16. So the total distance between the rails, the positive rail and the negative rail, can only be 16 volts, 32 volts. So if you want to have ground, then you can go up to 32, but if you want to split it, you got to go plus 16. It gives you a lot of other good information in this. So if anytime you have a question, all the detailed information is in here. I just wanted to share that. So you need, there's a database, and there are a lot of data sheet that you can refer to get whatever information you need. There are a lot of these op-amps out there. 741 is another one that is commonly used. Anyway, that's enough said on that. So what we're going to do, we're going to go back to our conversation. So let me just one more quick look at the data sheet before we walk away. So if you look at it inside this op-amp, this is the circuit now. We are talking about the fundamental of electrical circuits, so this is a little bit beyond the scope of what you need to do analysis right now, but this would be part of an electronic class where they're talking about transistors and analyzing it. You're not going to get into this level of detail. Instead, what we're going to do, we're going to use a simplified model which gets us pretty good answers in the DC space. The name of the model is called Ideal Op-Amp. We're going to make some simplifying assumption to let us move forward and solve more problems at this point without having to know all the details of the op-amps in terms of transistors and all that. We're going to assume that the gain is infinite under this model. So open loop gain is infinite. We're going to assume that the voltage difference between input is 0, which means Vp is equal to Vn, and we're going to assume Ip is equal to In equal to 0. So these are the 3 major assumptions. So if somebody says use the ideal op-amp to analyze the circuit, you can make these 3 assumptions. That's good to know. Okay. And now let's take a look at this thing. Op-amps are usually designed by having a feedback that comes to the negative side so the output doesn't quickly go to infinite. Remember, output of the gain is going to be open loop gain times any difference you have between VP and VN. So it could quickly go to the infinite side. So now, now they've asked us to analyze this circuit. Let's see what we know. We know this is IN. We call this one IN because it goes to the negative side. This is IP. And of the tools we have to analyze the circuit to find V out, we have basically KCL. KCL is usually the best tool to use for this kind of analysis. So we have to identify how many nodes we have. Of course, the reference node they've already given us. Then we're going to call this one VP. That's easy. And we're going to have this going to call VN. And then, of course, this is V out. Okay. Typically, this doesn't do us any good because, as you're going to see later on, we're going to have a hard time with knowing what I out is. So even though it gives us an equation, it adds another unknown. So it's really not very helpful to write this one. So we usually don't write the equation for this one. So let's go ahead and say we do a KCL. Again, I'm going to kind of take the shortcut here and say we're going to work, the units we're going to use is going to be volt, kilo ohm, and milliamp. This way I avoid carrying a lot of zeros with me. So if I do a KCL at Vn, you're going to find it's going to be Vn minus 5 divided by 10. That would be current flowing this way. Then I have a current flowing the other way, which is In, plus then I've got the current up here, which is going to be Vn minus V out divided by 5 equal to 0. So far, so good. And then the next thing I can do is I say KCL for Vp is going to be basically the voltage here. Well, you can take a look at that. So if you do this VP and you're trying to find that VP, is going to be minus 2 coming in plus IP going out, and then it's going to be VP over 1 equal to 0. Okay, so this is kind of interesting. It says I've got 1, 2, 3, 4, 5, 6 variables here, and I only have 2 equations, so I got a bit of a problem. But they told me that I'm using ideal op-amp. So what does that mean? Well, ideal op-amp, when I'm using ideal op-amp, that gives me a few equations. So ideal op-amp model allows me to say, okay, VP is equal to VN, so that's one thing I get, and then IP equals to IN equals to 0. Now A equal to infinite doesn't really do anything for this equation. It just tells me that I'm not limited by the gain of the op-amp, so I don't have to worry about it. So now if I take this one and apply it to this equation, that simply tells me that VP is equal to 2, right? Because IP is equal to 0 goes away and 2 goes to the other side. So that's great. So that basically tells me that then I know what Vn is as well, because VP is equal to Vn. So now all I have to do is I have to take this number and plug it up to the first equation, in addition to the fact that now I know In is equal to 0. So Vn is 2 minus 5 divided by 10 plus 2 minus V out over 5 equals to 0. Great. So cleaning that up, I've got minus 3/10 that can go, and then 2/5. So let's do a little cleanup here. Let's multiply both sides by 10. Both of these guys, top and bottom. So this is basically minus 3. So if I multiply, I get minus 3 plus 4 minus 4 V out, 2 V out. I'm multiplying top and bottom by 10, just clean things up. Okay, so I've got this, therefore that's going to be V out is going to be equal to minus 1/2 or plus 1/2 in this case. That's minus goes to the other side, become this is minus 1 goes to the other side. Oh, it's plus 1, sorry. Plus 1 goes to the other side, becomes minus 1, you get minus 2. So the answer is plus 1. You're not done yet. You need to find out if this value is below and above the negative. So the negative voltage is 5, the above is 10 volts, therefore we are in the linear region, as I mentioned. So it's not going to saturate. So indeed, V out equal to 1/2 volt is the answer to our problem. That brings us to the end of this, but before we take off, let's do a quick review of this. We introduced the concept of it, op-amp. We talked about the fact that op-amps either operate in 6 distinct regions. They are if you are below the negative voltage, then you're at the cutoff. You're not going to go below that voltage. If you are above, if your output tries to go above the positive bias, then this can't go, so it's saturated there. And then at this range, it's a linear region, moves up and down, and output is equal to A times VP V out when it's open loop. Then we said we took a look at an actual op-amp 4 in a package, LM324, and then we talked about one of the simplest models that works really, really well with the DC signals, called ideal op-amp. And when somebody tells you got an ideal op-amp, you get 3 things. One is the A equal to infinite, VP equal to Vn, and then IP equal to In equal to 0. Here is an example we did, and how beautiful it is. KCL is really the right tool for this process. So I would you can try KVL, but it's going to be very, very difficult. We wrote the equation of KCL, and then we came back around, applied the ideal op-amp, and we found the answer, and we made sure that the answer was within the linear region and was not cutoffs. So that was the last thing we did.